Today we're continuing with Hopf bifurcations, not both bifurcations, Hopf bifurcation, right? So last time, right, we defined what a periodic orbit is, what is an isolated periodic orbit, right? So it's just by itself and not isolated. So they're a continuum of periodic orbits, one into another, like concentric circles. And I sketched this type of bifurcation where you have, kind of like an equilibrium that is attractive, but it's a spiral, right? And then at the bifurcation point here, this spiral breaks into many periodic orbits, non-isolated, right? And then after, as the bifurcation parameter increases, this equilibrium that is always on the zero axis with red becomes unstable. So that was the kind of the picture, but I said, okay, let's do it, let's write the system and see what how we deal with this one, right? That's what we were, where we're left. So here is the standard form, normal form of a Hopf bifurcation. Okay, I should move that. Yeah, okay. So it looks something like this. So we need two coordinates, you see, because the picture is about periodic orbits. We see them in XY coordinates, right? And then it's not like the other bifurcations where we had just X, right? And the parameter. So here, if you want, is X and the parameter and the epsilon, right? Epsilon and the X. Here, for the Hopf bifurcation, we need two axes to see it. Okay, X and Y. All right, so this means we have a system in 2 dimensions. So here it's this fellow. So that's kind of the normal form of it. So it can be brought to the first, second order terms and third order to look like this. Okay, so we're going to write it as a system with matrices. So here is the linear part, X and Y. So here I'm going to input some coefficients. So we have an epsilon, -1, 1, and epsilon. Okay. And then these other nonlinear terms. Okay. Now, when we're looking for equilibria, okay, so immediately we're going to notice that we have an equilibrium at X, C, Y, E. I'm writing it on the vertical this time, 0, 0, okay? So this is no matter, for all epsilon, no matter what epsilon is, right? So for all epsilon here, you can see actually on the first one that if I put 0, 0 for X and Y, we get 0 on the right-hand side right there. Okay, so when we're looking at the linearization, right? So the matrix, the linearization matrix, no matter what it is, we can do it at 0, 0, we can do it wherever, okay? This is, we'll end up with epsilon -1, 1 epsilon. And now we're doing the eigenvalues. Right? So we end up with epsilon minus lambda, epsilon minus lambda plus 1 is 0, right? So epsilon minus lambda squared is -1. So epsilon minus lambda will be plus minus I. You see how I'm solving it? I'm not doing now the entire quadratic. I'm just taking advantage of this form, right? So now we can say that lambda will be epsilon plus minus I, or minus plus I, right? So if I'm keen about the signs, right? Okay, good. So we see that the real part of the eigenvalues, so this is lambda 1, 2, if you want, is epsilon, okay? So now we have if epsilon is negative, so this real part of lambda is negative, then the 0, 0 is a stable spiral. Okay. Okay. Yeah. So it's spiral because we have that I there anyhow, right? So it will be a spiral no matter how we put it, or a center. So now if epsilon is 0, so this guy is 0, then we have this equilibrium is a center. And finally, if epsilon is positive, then the equilibrium is an unstable spiral. Okay. And this is really the picture that we drew last time. Okay, so we have 0, 0 as the equilibrium for all epsilon. So I'm waiting for you to write, and then I'll flip back to the picture. Okay, so 0, 0 is an equilibrium no matter what epsilon is. And then we have, you know, a switch of behavior at epsilon equals 0. Up to epsilon equals 0 is a stable spiral. From epsilon equals 0 on positive is an unstable spiral. So let's look at this picture now with this side. So we have 0, 0 as an equilibrium for all epsilons. That's what the red line is, yeah? And then up to epsilon equals 0, which is here, right? So this is, if you want to know, epsilon equals 0, I want to say 0. Okay. We have up to here for epsilon negative, any point on this red axis, if you want, is an equilibrium that is a stable spiral. At epsilon equals 0 is a center, and is a switch point from a stable spiral to an unstable spiral. Okay. So this is a typical Hopf bifurcation. Okay, and it's encountered in various applications. Okay, so that's one item for the day. I hope it's clear. I will ask you to recognize this kind of stuff. So essentially, you know, this Hopf bifurcation involves, you know, a spiral of some sort. The switch is its, you know, stability. Okay, fine. All right, so everything is, again, you know, pops down to eigenvalues, right? That's the thing. Okay, so unless you have a question or something, I'll move on, because that's it with this topic. So you have the 4 types of important bifurcations that are encountered for the systems with one parameter. So this is just one epsilon, okay? So they have saddle node, we have the transcritical, we have the pitchfork, and for 2x2 system, you have the Hopf one, right? The switching periodic orbits. So that's it. And then you can ask me, you know, what happens if you have 2 or more parameters? Ooh, it's a can of worms, right? Because you can have bifurcation. So you see here, we can represent the parameter as a, right, on one axis, right? So it's a curve that then we straighten if you want, right? So it's just one axis. But if you have 2 parameters, then, you know, you could have surfaces of equilibria for each value of these parameters. And these surfaces in space, they don't have necessarily be nicely, you know, nice sheets like we talked about submanifolds. They could be twisted and turning, and then, you know, it's quite a thing to understand what's happening, you know, as you go from a level to another, because you'll start having holes and stuff like that. So beautiful, beautiful subjects for studies in grad studies. Okay, so, you know, and there is no as far as I know, no simple classification of these bifurcations of two or more parameters, right? So actually they're called, so when you have a one parameter, they're called codimension one bifurcations. That's what we did, you know, and then codimension two and higher, things are becoming more complicated. Okay. All right. So that being said, we move on to, I want to work with you passing to polar coordinates, because I know you had this in your assignment and you loved it so much, right? So I have an exercise with passing to polar coordinates. Actually, it's really this system. So let's do it as a, so you have a model or two about how to work passing to polar coordinates. Okay, so I'm going to just for x, y to r theta, and I'm going to work it out actually on this system that we just had, because I just have, and you'll see what nice thing is happening actually once we pass to polar coordinates, because after all, this switch point where we had these circles, right? These orbits one into another. Obviously, there is something like a decoupled in between r and theta as coordinates, because you know r just stays the same, right? Whereas theta moves in a circle, where r, you know, is the radius of the circle. So that should become apparent if we are going here into polar coordinates. It's also, you know, like a kind of winking around this x squared plus y squared, which is nothing else but the radius squared, right? So it's like wink, wink, you know, maybe if you pass to polar coordinates, something nice will happen. So here, right, is the standard r cos theta and r sine theta. Now I have to say that, you know, to be precise, r has to be positive, okay? R in zero is not a good, so this map has to be well defined back and forth, right? You know, it should be injective and surjective, right? So, but at R equals zero, theta can be anything. So that's why we exclude it, right? Whereas theta, okay, here we can think it's in between 0 to pi or on a circle, and then, you know, we just take, you know, the circle as equivalence class and whatever. I don't want to go into, you know, topology or whatever. Okay, so this is this. And then the other way around is R is, right? So I'm writing these things that you know very well. And then tan theta will be y over x, yeah? Okay. So now I want to go from xy to r theta. So I'm going to compute r dot, right? So r dot would be, if you want, d b dt of this guy. Okay, and now I'm going to do the job. So d b dt, right? So the dot is a shorthand for d b dt. So whenever we're doing this kind of calculation, we just have to remember that x is not just x, is x of t. So we have to do the chain rule, okay? So here is 1 over 2 root of, from the root derivative, but then on top we'll have 2x dot plus 2y dot by the chain rule, okay? And now I'm going to substitute there. Okay, so 2 is going away. I'll just cut it like this. I won't write another line for you for it. And now x dot, y dot. Okay, so we have to substitute all these guys with what they are. So x is x. I'll just do it like this first. Okay, and x dot is epsilon x minus y plus, now I'm going to mix the notation, but it's okay. Okay. R dot, r squared x plus y, x plus epsilon y plus r squared y, everything over 2r, right? Okay, and now we do the computation in there, and some miracles are happening. Epsilon xy, so this guy is going with this guy, and then, okay, did I do something? What else is going? Mhm. Okay, so let's see what we're left with. So it's a epsilon times x squared plus y squared. Okay. Plus r squared times x squared plus y squared. Everything over 2 r. No, there is no more 2 over r. Okay. So it pops out as epsilon plus r squared times another r squared over r, right? So this means that r dot, right, now I can collect it, will be r times epsilon plus r squared. So if I'm doing any mistake, please put it in the chat. I did the calculation before, so I hope it's correct. Yeah, you see how beautifully it pops out this one. And now for the theta, what I'm going to do, I'm going to take this one and I'm going to do the derivative left and right. So this is 1 over cos squared of theta. Theta dot, I keep telling you, these all are functions of t, okay, is, right, so that's a fraction, right? So y dot x plus, not plus, minus x, y, okay. Okay, minus x dot y over x squared. And now if you substitute here, so substitute y dot and x dot, okay, and x and y. Okay, I will not do it. I'll let you finish it. You're going to end up with theta dot is 1. Okay, so it's exactly sub like we did it for the r dot. Okay, so you see how beautiful this system actually, right? This guy here turns out to be this, right? And now I can look at this one and make a, you know, an analysis of it, right? But I'm not doing this now, okay? But anyway, it's beautiful, isn't it? Okay. With this being said, so, you know, I mean, we can continue here with theta of t will be just t plus a theta naught. So it's always the same motion in theta, right? And then for r dot is just telling you how the radius, the length of the radius vector varies, right? And actually, if you would you do an analysis of this, you'll see that, you know, r dot is decreasing and increasing. That epsilon is 0 is actually a bifurcation point. So I'll let you do that. Maybe to prepare your final, okay? Because it's like the next equation. All right, so with this being said, okay, I'm going to move on to this thing with the central force problem and stuff related to your homework. So I prepared a couple of pages that, you know, I'm trying to bring things in the context just before attacking that problem that you had on your assignment. Okay, so, you know, the way to model this rocket scientist, you know, rocket science and planetary problems, of course, you start with the non-trivial easiest problem. And then the easiest problem that one can think of is the so-called the relative two-body problem, or starting with the two-body problem, actually, and in which you have two mass points. So I call them P1 and P2, okay, in a system of reference. And then you know that these guys attract each other with a force that is directly proportional with some constant that people call gravitational constant, the product of the masses, and inverse proportional with the distance in between the bodies squared. So now if these two mass points, right? So when I say a mass point is an ideal object, right? It's a point, like a little dot, in which the entire mass of that object is concentrated, okay? So it doesn't have physical dimensions. It's just a point, but it has, you know, this quality that it has a mass, right? And then it also puts out this gravitational field, okay? So here are these two mass points. You can think Sun and Earth. You can think Earth and the Moon. I don't care. Okay, so just two mass points idealized, right? So Sun and Earth idealized at points. And we have this rough idea of how the force is, and then Newton told us, you know, mass times acceleration is the force, and that's exactly we have to start modeling now. So here are the two mass points. Their radius vectors R1 and R2 in some 3 dimensions, right? So we want to really describe the motion of each of these points, okay, R1 and R2 in time. So to do this, we really write, you know, mass times acceleration is force, right? So we know that, for instance, P1, right, is attracted by P2 with a force that I call 2-1. So it's the effect that body 2 has on body 1, okay? Whereas force 1, 2 is the effect that body 1 has on body 2, just in case we go and model more bodies, because then we have to keep track of these indices, right? And we know that, you know, they're equal in size, but they're opposite in direction, okay? So by the way, if these two bodies would stay on a line, right? So I just release them, like I put one here and one here, and I don't give them any impulse, any push a bit off this line, what they will do, they will fall one into another, because there is nothing to you know, divert this motion from one into another, right? So in other words, what I'm trying to say, if I have two bodies on the line and I give them, you know, even velocities along this line, no matter if it's outwards or inwards, they will, you know, either separate, or if really, you know, I push them really hard, but this is to be seen from the analysis, or they will fall into another, right? So the only way these guys won't fall into another, like we don't fall into the sun, is because of the rotation. And I did explain this to the guys in the other course, right? So this rotation is like the centrifugal force that we have in our dryer, right? So when the clothes are wet, we put them in the dryer. What does the dryer? It spins them. When it spins them, the centrifugal force, right, it just pushes the water out of them, and that's how they get dried, right? I mean, well, there's not the dryer, actually, there's the spinner. The dryer, yeah, the dryer is with air, sorry about it. So it's a spinner, right? It's how to take the water out of clothes. So that's exactly the phenomenon that, you know, stops us from falling into the sun. We rotate around the sun, and there is this balance in between the attractive force of the sun and the push out of the inertia of the rotation. That's the physics of it. Now, how the mass goes, that's, you know, that's a different story. And it's not trivial. I know it's not trivial, but it used to be done in all maths programs until about 20 years ago, you know, then it disappeared. I don't know. Okay, so here are the equations of motion written roughly, how they look. Okay, now I'm expanding them. So one is opposed to another, right? So they're equal in size, but they're opposite. So this means when I'm adding them, like I'm adding this plus this and this plus this. On the left-hand side, I get what I get, but on the right-hand side, I'll get a nice 0. So then whatever is on the right-hand side in time, these are functions in time, right? So you have this, a function in time is 0, then its antiderivative, if you want, is a constant, right? So the antiderivative of the acceleration is the velocity. So this product of mass and velocities here, and then it's a sum, is constant. It's a constant vector, if you want, right? Because they're vector quantities. And what is that constant? Is what it was at time 0. These are called constants of motions or integral of motions. They're exactly like the energy integral that we discussed in harmonic motion and you had in your assignment, right? It's the same thing. So there are these constraints, right, that are in the geometry and the physics of the problem. And then they help us when we want actually to solve something because, oh, look at them. So these guys, right, they stay constant in time. Oh, now actually I can integrate once more this thing, so do its antiderivative once more, and we end up that this quantity, which is nothing else but the center of mass without all the mass under it, okay, so it's almost like the center of mass, you know, moves on the line, okay, with constant velocity. That's what it says. It moves on the line. What line? the line AT plus B, if you want, right? With constant velocity, right? Velocity A, right? And these quantities A and B, these vectors, they're known because they're given by the initial conditions, okay? So why is this useful? Well, we can think like this. If I know one of these R's, if I know R2 somehow, then R1 will be AT plus B minus R2, right? So it's sufficient to know one to know the other one, right? That's, okay. Or it's sufficient to know the difference in between them, which I called here the vector R, right? The relative distance, right? Because then once I know this guy, right? And then with this relation here, right? I will have a system, two unknowns with two equations, right? R1 and R2 are the two vector unknowns, and I'll have their sum weighted by the masses is known, and then their difference is known as well. So, you know, I'm in business. Actually, in physics, where they do experiments and stuff, I think, you know, this frame XYZ that is outside of what you're measuring is called the lab frame, right? Whereas when you're sitting on one of these things, right? So you're moving with the stuff, right? So actually I should put myself in the center of mass of these two guys. So let's say it's here. Okay, so I'm sitting here. I think this, I don't know the name of that, actually, I don't remember. I remember only the lab name. So yeah, the point is the following. This integral of motion, the center of mass, actually it's called integral of motion, allows us to actually reduce the problem from two vector unknowns, R1 and R2, to just one of them. So I could choose one of them to be R1 or R2 or the difference of them, okay? So if I know, I repeat, if I know this R on the right here, okay, and I know this relation here, so I know this in time, how it evolves, I know this how it evolves in time, then together they will allow me to solve for R1 and R2 separately, okay? So it's sufficient just to solve for the difference, and that's the point. So I'm gonna go now to the difference. Ta-da, okay? So let's see. Oh, actually I wrote all this story that I was telling you about. I don't have to go about it again. All right, so I'm going now to the difference. Okay, so here are the equations of motion. They're the same that we had before. Oh, I noticed that actually I can cut some of these masses because, by the way, these are always positive because we're talking about the problem from physics and not just invented. We can have negative masses if we really want to play. Okay, we subtract these equations one from another and look what a nice ODE we get with vector R of t as unknown. So that's what we want to solve for, okay? And of course, we're going to assume that we have some given initial conditions, okay? So we'll have an initial velocity if you want, and we'll have an initial, an initial position and an initial velocity, okay? So it's a ODE, second order, We have many unknowns because there are 3 positions and 3 velocities, so there are 6 of them. And the ODEs is terribly, terribly nonlinear. That's the way it is, okay? But people, you know, didn't give up and say, okay, maybe we can say something about this. Maybe we can try to solve it, okay? So let's see what, yeah, what it led to, right? So here it is again, right? I actually called it, put a name on it, the Kepler problem. So in this respect, you know, we're gonna look at the problem, right? So let's say this is the Earth here, this is a satellite, okay? Here is the equation of motion as we had it. But now let's say that the satellite, right? So the mass of the satellite is so small that it doesn't really count for anything. So we end up in here, so I'll make this one to be almost 0. I'll end up with this equation. And in this equation, I'm supposed to shift the coordinate system, right? So it's in the center of the mass. I'm gonna supposed to shift it in this Earth, right? So it will be here, right? There I go. So I can actually take these fellows out of here, okay? Well, we'll do the picture again. The point is that, right, we end up, you know, with this nice equation here. I wrote it on the 3 coordinates, okay? I repeat, we have given some initial conditions and some initial velocities, and then, you know, we have to do the mumbo jumbo to see what is going on. And with this thing, I'm going to move on to what I want to do today with you and actually start with the more general problem, okay, that is related to this one. If you look, see this one here, okay. This one here is a particular case of this problem. So f of r, right, on the other page was mu over r squared, right? There you go. Okay. So that one is a particular case for this one. So these are called central force problems. So what is going on, you know, is basically you have it's called a gravitational source like the sun or the earth, right? And then you have this point around it, which is attracted by this fellow. Okay, so it comes with this attraction that is always pointed towards the gravitational source. So in this case, chosen to be the origin of the system. Okay, all right. And these central force problems have a commonality, okay? They share some properties together, so that's why. And then, you know, we're gonna take the particular case with the gravitation. There's just a particular case of this. So there you go. Okay. So the first thing you had to choose to show in your problem, so here I'm gonna say assignment 3, right? Okay, problem 3, okay, I'm gonna do A, right? So the first thing was to show that, okay, if we write this guy like this, right, V dot is minus, okay, that the energy is conserved, okay, so the energy was defined something like this, right, plus V of R, where V of R is the potential, right? Okay. Now, what means the potential, right? So I missed a sign and the other problem. Okay. So the potential has the wonderful property that V prime of R is minus F of R if it's in 1D, right? Okay. But here, what we have to take the gradient of V because R, right? In this case, R is something like this. So we have to take the gradient of V. and compute it. And this one would be something like minus f of r over r. And that was part of exercise 2C or something, and I'm not doing that. So in there, you had to show that if you have a function that depends on the radius distance only, then when you do its gradient, you get this kind of formula. Okay. So to fix this idea, okay, so for example, if you have v of r is 3r squared, where r is actually root of x squared plus y squared plus z squared. What is gradient of v? Okay, you can compute it like, so it will be dv dx, dv dy, dv dz. But once you do this job, you're gonna notice that this one is actually the derivative of v times r over r. So this will be like 6r times r over r. This is a property of these guys that depend only on the radius distance. Okay. So if I have here in another example, I have v of r to be ln r plus 6r2, I don't know, plus 1. What is gradient of v? Okay, it will be 1 over r plus 12r times r over r. There are various proofs for this, you know. The most direct is to do it by hand in general, and then, you know, it's like ask you. But that's a nice property of this kind of functions. Okay. Have you seen it before? You can put in the chat. Okay. All right. So there's that. So I'm going to go back. So obviously here r is positive. So in this case, things, you know, r is always positive, right? It's a distance and it cannot be 0, as I was saying, from polar coordinates. So here, essentially what I was saying, look, you know, when you do here dE or dt, because that's what you have to do, okay, this would be 1 over 2 v times, okay, 1 over 2 2v v dot, and then plus gradient of v of r, if you want, times r dot, because we are always applying the chain rule. And that's what you have to do. And then we substitute this v dot and r dot with what they are from the system. And that's how we verify that something is a conserved quantity, right? So this was, we did it for the harmonic oscillator. Actually, someone asked me today, so you can find it in lecture 7, page 3, when we verified the energy conservation for the harmonic oscillator. Okay, so now here I'm continuing this. So this would be v times v dot is minus f of r, r over r. Okay, no, v, not v dot. Okay, okay. And then plus this guy, right? So it's v prime of r times r over r. And then v, right? And this thing, right, this has to be f of r, right? So that's where I messed the sign in your assignment, but you know, that was, if you did this, you get a bonus, as I promised you. So this should be 0. So in this way, we get that this energy along any solution will be a constant, as I wrote there in your assignment. Okay, that was what I wanted to see, actually. Okay. All right, guys. So this was in the spirit, I repeat, to the energy conservation of the of the harmonic oscillator. Actually, the harmonic oscillator is another particular case of a central force, actually. That's another one. Okay, for point B, this is, life is much simpler, actually. Okay, where did I put that? Ooh, I put it up there. Okay. So you had to show in point B that R, so I wrote there R of t times V of t, right, is a constant that I called it C, right? So that's what you had to prove, okay? So here, I put R of t, you know, I'm putting it R of t just to make a point that you have to think that this is along the solutions of this given system. And it's not just R with no evolution, if you want. So here is that system. So I'll need this equation, okay? So I'm going back to the equation as it was written initially. And here how the beauty starts working, okay? So what I will do, I will cross product both sides by R, okay? So when I'm doing this, we get on the left R2 dots cross R equals minus f of R cross R over R. Woo, but I remember that R cross R is always 0, right? Okay, so what does it mean, the cross product, right? If you have two vectors, I remind you for multivariate calculus, right? So I have a vector and another vector. I do this or times this, right, is the vector that is given by the right-hand rule and is perpendicular to the given 2, right? That's how we find it, okay? And there's a size, its size is the area of the triangle formed by the initial two vectors. Okay, so I repeat, you know, so the cross product of two vectors is a vector itself that is perpendicular to the plane of the plane of the given 2, and its size is the area of the triangle formed by the initial two vectors. The cross product of the same vector with itself is 0 because this means that the vectors are parallel. Okay, and then there is no area to discuss about, okay? So that's from multivariate calculus. So this guy is always 0, so we end up with this for any t if you want, okay? But now this one is nothing else but dB dt of R dot cross R. Okay, so if we verify indeed, because what would be that one would be R2 dot cross R plus R dot cross R dot, right? But this is 0. So indeed, whatever I wrote there is, so indeed this guy is this guy, right? Okay. So this means that now I can switch this the other way around. If it's 0 is 0 both sides, right? So we have that R cross R dot is a constant vector for any t. Okay. So what constant vector? Oh, if you want me to specify it for you, is the R at time 0 cross R dot at time 0, right? But it's constant. It's like the energy. It's a conserved quantity. So we can call it an integral of motion, or we can call it an integral, a constant of motion, or we can call it a conservation law, right? They all mean the same thing. Okay. So this is a side note. Okay, so now we said further, you know, if C is 0 or C is non-zero, right? So if C is not 0, I said show that the motion is on the plane. Okay, so we have R cross R dot equals C. All right, so let's do the triple cross product left or right with R, let's say. Now I do remind you when we're doing such a thing. So, right, R dot C, okay. When you have the triple product and two vectors are the same, this is always zero. Why? What is the meaning of the triple product? Is the volume formed by the three vectors. The volume of the uh, parallelepiped, right? That is formed by the three vectors. So if I would have VWS, you know, the triple product would be the volume of this thing. Now, if two of the vectors are the same, then the volume is zero. And that's exactly why this is zero. So I do remind you here, I should make it here, right? So if I have V, something like this. Okay, so here is a V, a W, and an S. If I do V, W cross S is the volume. Okay, is the volume of this thing. So now obviously if two vectors are the same, the volume is zero because that becomes flat, right? So that's why. All right, so I'm going back to my relation here. I'll flip the page. So here I'm in this, if C is non-zero, right? So we had R cross R dot or V, doesn't matter, okay, is C, right? And I said, let's do the dot product with R. And we ended up with R dot C equals zero. Oh, but this means that R of T will always be perpendicular to C for all T. And this C is a constant vector, it doesn't move. C is frozen, right? So that's one. Now, also we have that coming back to this one. Now, if I do the dot product by R dot, we're going to end up again with something like R dot, R cross R dot is R dot dot C, okay? And again, this will be zero because it's the same idea of the volume if you want. Calculate it. So this means that we'll have R dot C to be zero for all T. So in other words, the velocity now is perpendicular to this constant vector for all T. Oh, okay. So the motion now, if I want to do it, is something like this. So here is X, Y, Z, and I'm going to make this thingy here. And here is my radius vector. It just stays in this plane for all values of T, okay? So I would have an R at, if you want, T0, and then an R at T1, and then an R at T2, right? And the velocities are in the same plane, as this one that I drew it with green, okay? So here is a velocity, here is another velocity, here is another velocity. I'm just doing, like a tangent to the path, huh? Kind of, all right? And where is my vector C? Oh, this guy is perpendicular and fixed, right? Here is C. Okay. And at all times, we have this perpendicularity, if you want. Okay. So the motion always is in a plane. Okay, in other words, you push a satellite up there, right? And you give it a push, it will stay in the same plane all the time. It won't wobble. If it's at the level of the equator, it will just go around the equator. It won't wobble up north and south. It will just stay there, right? If you put it inclined, it will just do it inclined. Well, the worst would be perfectly round, but it's not. Okay. So that's the thing, all right? So now we had also, if the case when this constant was 0, right? So we had r cross r dot to be 0 for all t. Oh, okay. So if it's 0, right, this is possible if and only if the vectors are collinear, right? So we sell them parallel, okay, i.e. they are on the same line, right? Because the velocity vector is attached to the point, right, to the position. So they will be on the same line. Okay, that's it. All right. So that was point B. In point C, you had to go to the polar coordinates. There you go. You'll see how beautiful of a calculation I made of this one. You will love it. Okay, so the point C was, here is, okay, so first it was like without losing generality. So we have that C is non-zero. So the motion is planar. Okay, so if it's planar, without losing generality, choose X or Y to be the plane of motion. Yeah, okay. All right, so I'm going to ignore the Z axis. I don't need it anymore. And everything now happens in a plane. Okay, X, Y. So here's our guy, R. Okay, and now R is just an X and Y. Okay, because it's no point to say to have the z-axis considered. All right, so now with this equation, right, so this looks like, right, so we have r dot was v, v dot was minus f over r over r, right, which in components becomes something, or, okay, however you want to do it, right, so, okay. So this is as a second order. And now when we're writing this guy as x two dots and y two dots, right? This would be minus f of r, which I'll put it directly over r, f of r over r. Okay, and now vector r is actually x and y, right? So in other words, right, if we write it, it would be something like this. And y two dots. So that would be in Cartesian coordinates, right? Over r, where r is root of x squared plus y squared. Okay, everybody is with me on this one. There is nothing wrong, nothing hard. I'm just rewriting the problem in plane, and I'm rewriting the equations of motion. And now comes the hard part. We have to pass to polar coordinates, right? Okay. So I'm going to flip the page. Okay, so how is it? So I have x, two dots. I'm going to write here what I need, okay? Okay, let's make it like this. Okay, and then y, two dots. F over r, y. Okay, and now I'm going to go, so I want to do xy to pass to r theta. Okay, where, okay, we have to be organized because, okay, x is r cos theta and y is r sine theta. And I keep telling you, x and y as r and theta will be all functions of time. So whenever I'm doing a derivative, I have to take into account the chain rule. Yeah. Okay. So I'm going to start writing these things as a in matrix format, and you'll see why. Okay, so x dot y dot. So x dot, I have to take this one and do its derivative with respect to time, okay? And r and theta are also functions of time. So this will be r dot cos theta plus, actually minus, r theta dot sine theta, yeah? So that's the x dot. Okay, so r dot cos theta, and then cos theta derivative is minus sine theta. So I put the minus in front. R stays, and then when we do the cos theta derivative, we have the sine theta, but we have the theta dot because it's chain rule. Okay. What about y dot? It's there, right? So this would be r dot sine theta, and now plus r theta dot cos theta. Okay. Or I could write it like this. So it's cos theta minus sine theta, cos theta, r dot, and r theta dot. And I kind of recognize in that matrix there rotation of angle theta. That will count later. You'll see. It's very beautiful, actually, what happens. Okay. So I'll make it as a side note. So this is actually a rotation of angle theta, right? So I can say it's a rotation of angle theta. All right. Now let's do x2 dots and y2 dots, okay? I'll need more space now, I think. Okay. So this is a product. So it's the product rule, okay? So first I'll take the derivative of that matrix, which consists in taking the derivative of each term, and then not forget to put the theta dot, okay? So I'll put the theta dot at the end, okay? So cos derivative is sine, oh, with minus, right? Minus sine, then minus cos, then cos, then minus sine, and then is the theta dot, right? Okay, so I can put it in, I can leave it out. I'll have to put it in actually, so let's put it in with r dot and, yeah, so r dot theta dot and r theta dot squared, yeah? There's that, okay? And then plus, now this guy stays the same, and then I have to do the derivative of the other guys, right? So here cos theta minus sine theta, cos theta, and now the derivative of this guy. So r dot derivative is r2 dots, and this one here is I have two terms, right? So r dot theta dot plus r theta 2 dots. Okay. All right, so what is next now? Okay, so this is, right. First of all, so this still stays, right? R of theta, we'll need this. That's why I keep doing this. Where this one here, if we're, you know, quick to look at it and do some mambo, I really want to see them as rotations. And why do I want to see them as rotations before moving on, you know? Because when I have a rotation of angle theta and I multiply it with a rotation of angle minus theta, this is the identity, for instance, okay? That makes my life much easier. If we have a rotation of theta 1 times a rotation of theta 2, this is a rotation of the sum, right? So if you rotate an object by an angle in the same plane, and then by another angle, it's a rotation of the sum of the angles, right? This makes the rotations, gives the structure of an algebraic group, okay? If you ever took the group course, right? Algebra, abstract algebra group, right? Rotations are actually a group, and it's more than a group, it's a continuous group. It's beautiful stuff. So now I'm coming back to here. This one, if we are gonna check it out, actually we will discover that is a rotation of angle theta minus pi on 2. Okay, and this is because, for instance, any sign can be seen as a cos of pi on 2 minus theta. Okay, and then, you know, with the minus in front, you change the minus again and you get up there. So, you know, anyhow, I'll let you figure out that actually this one, it is a rotation of angle theta minus pi over 2, provided that the general definition of a rotation matrix is this one. Okay. Yeah. So now coming back here, I can write, so I'm going to isolate this fellow. Okay, so I'm going to take just this term and then say, okay, so this term, which is r of theta times r2 dot, and then this stuff here equals r of theta minus pi on 2, then r dot theta dot, and then r theta dot squared. And then we have to subtract that x2 dot y2 dots. Okay, so I'll write it like this now. And then we have to figure out what this fellow is, as is defined up there. Okay, so we'll do the 2 dots business on it. Okay, and actually, no, I'm silly. It's not that one that we're going to look. We're going to take it from the equations, right? So this one, okay, we're going to take it beautifully from the equations. Okay, so instead of writing x2 dots, y2 dots, okay, I'm going to take this one out. Okay, I'm going to write instead of it, I'm going to leave these guys as they are still. Okay, and then minus f of r over r, and now x and y, and x and y, I'm going to take them as what they are, right? So it's an r as well, and then cos theta and sine theta. Isn't that beautiful? It's just gorgeous, I think. This is my taste. Okay, because I'm avoiding long expressions. I'm just using some other stuff, right? You know, rotations. Okay. All right. So, okay, I'm going to take the green part again away because I don't want to flip the page yet. Okay. So r with r is going away. Yeah. And then I can isolate this stuff. So it's r2 dots, and then r dot theta dot plus r theta 2 dots is r minus theta, right? So I'm multiplying by the inverse of r of theta, which is r of minus theta, right? Because that was with the green stuff under there, right? So a rotation theta, its inverse is a rotation minus theta, of course. Yeah, okay, good. Okay, and then r dot theta dot r theta dot squared, and then minus f of r, and then this r of minus theta is applied to cos theta and sine theta. So now these guys, okay, this is a rotation of angle minus theta plus theta minus pi on 2. So it's actually a rotation of angle minus pi on 2. So what is this? Okay, so let's put minus pi on 2 instead of theta in the definition of a rotation, right? So cosine minus pi over 2, 0, right? Then 1, then minus 1, and 0. Okay, so let's see where we are, okay? So here, we're almost there. So R2, what did I do? Okay, I don't want that one. Okay. R2 dots, and then R dot, okay, theta dot plus R theta 2 dots is 0, 1, minus 1, 0 as applied to R dot theta dot and R theta dot squared. And then minus f of r, and then I have to write this thing. So that was a rotation of angle minus theta. So that just changes the sign at the sign, at the sine function. Okay, because cos minus theta is cos theta, so we don't have to do anything there. And then this is applied to cos theta and sine theta. And let's see what we get. Okay, we're ready to score. So R2 dots. Okay, yes. Okay, so from the first line, we have an R theta dot squared minus f of r times cos squared plus sine squared. Isn't that a little miracle going on, huh? And for the second line would be minus r dot theta dot, and then minus f of r times minus sine cos plus cos sine. Miracle! It's a miracle. It's okay. And this is 1. Oh, I'm getting goosebumps. Okay, so there you go. R2 dots is R theta dot squared minus f of r. And then R dot theta dot plus R theta 2 dots is minus R dot theta dot, because this is 0. I cannot breathe anymore. Give me some water. Oh, I got it. I got it. Okay, so there you go. So at some level, that's what you should have gotten in that homework of yours. And that beautiful, huh? But I had to go, over there. Of course, any other solution, as long as it's correct, is a good solution, okay? This is the kind of solution I kind of like it if I really have to do this job in this way. However, mechanics is gorgeous. And as a matter of fact, maybe next time I will tell you how people invented a way to avoid these calculations and just do them like at the flip of a finger, okay? And that's called the coordinate independent formulation of mechanics. And it's independent for mechanics in classical context, in quantum, in relativity, and is done via the so-called Lagrangian mechanics, okay? And then Hamiltonian. But anyhow, one has to go through the pain of this kind of changes of coordinates in order to really appreciate the formulation that is independent of coordinates. See what I mean? Yeah, okay. So that was point, whatever point. So this means that next time, because I think you're tired. Why do I think so? It's also, the time to finish the lecture. Next time, we're going to take this stuff and we're going to go with the equation where we have really the gravity. So what we did until now, as you can see, is a kind of independent of that central force, right? So actually this conservation law and the fact that the motion is planar, is independent of what the force is, can be gravity or not, right? Okay, so that's for any f of r, as long as the the formulation is this way, I can put f of r to be whatever I want, as long as it's a function of r only, right? Okay, that's the thing. So here there are all kinds of problems that consider perturbations of the gravity, and they add, effects of, oh, the space is a little bit curved, so then we're going to put another term of 1 over r at cube, or, oh, the earth actually is flat a bit, so we're going to have perturbations that in the equatorial plane really look like something over r at cube. And those guys, so we'll have a f of r that is like mu over r squared, and then another term that comes with r at cube that would show up as a gamma over r at 4 in the f, so I'm always thinking in terms of potential. But the point is that, the theory of the central force stays the same, right? So it's a classical subject in a way, And now, next time we're going to see how come we have these satellites and these GPS is whatever is up there, and they don't fall on us, and they don't go away either. How come they're sitting up there? Well, they're not really sitting, they're moving with us. That's the thing. Okay, fellows, and on that note, I'll see you next time, and take care, take advantage of the weather. Okay, so see you later, okay?